Hello and welcome back to Unbounded Operators, the video series where we talk a lot about some nice topics of functional analysis. And indeed, in today's part 5, we will continue with the closable operators by looking at an example. But you might already know, before we can do that, I first want to thank all the nice people who support the channel on Steady, here on YouTube or on Patreon. And please don't forget, on these platforms you find PDF versions, quizzes, and early access to all new videos. Okay, then let's start this video here by considering a closable operator T. And there you already know, for the definition we need two normed spaces x and y. And at this point I can already tell you, in order to get nice theorems out, we have to assume that x and y are Banach spaces, so complete normed spaces. In fact, also in this example today, we will take Banach spaces. But let's first write down the general sequence characterization for a closable operator. There, we just have to look at sequences that converge to the origin, and they have to have the property that the images also converge. And then the conclusion is that only the zero vector in y is possible for this limit. Therefore, please remember here, if we have this implication, we know that the operator T is closable. And this is exactly what we now apply to the following example. And in order to make it very concrete, let's choose a very nice Banach space for x. Namely, x should be given as lowercase l2. So you know this is a space of sequences with index set n and entries in C. And please recall from the functional analysis series that this is a well-defined Banach space. Moreover, it's even a Hilbert space, but this is not so important right now. Okay, in addition, let's also fix the canonical unit vectors denoted by E1, E2, E3 and so on. Now, if you don't know them, then maybe very quickly, E2 is given as the sequence 0, 1, 0, 0 and so on. In other words, everything is 0 in the sequence except the second position, which is a 1. So you see, this is exactly the same as you would have it in a finite dimensional vector space, but now in infinite dimensions. Okay, and now I want the operator T going from x to C. And obviously, C is also a normed space, even a Banach space. Then, in the next step, I want to define the domain of T. And this should be given as the span of the canonical unit vectors. This means all the linear combinations of the canonical unit vectors lie in the domain of T. And here please note, this is not equal to the whole space X, but it's a dense subset in it. Okay, and now this domain makes it very easy to write down a nice definition for an operator T. Namely, we just have to say what D does to a canonical unit vector. And for example, we could just say, take the corresponding index of the unit vector. Therefore, T would send E2 to the number 2. And now since we want a linear map, the extension to the whole span here is uniquely given. But for the sake of completeness, let's write it down. So let's say we have a finite linear combination lambda j times ej. So please note, this here is always a finite sum, because this is what the span means. It means the set of the finite linear combinations of these vectors. And therefore the mapping here is totally clear, we just add up lambda j times j. This gives us a complex number, which is the output of T. Okay, and the first question from my side would be, is this an unbounded or a bounded operator? To answer that, we can just calculate the operator norm of T. By definition, this is the supremum over all inputs x with norm 1, and then we look at the norm of the images, which in this case is the norm of C. But of course, the norm in C is just the absolute value of complex numbers. And now let's say, instead of every vector x, we just put in the canonical unit vectors. Then the whole supremum cannot get bigger. Then everything is much simpler, we just have to calculate the absolute value of Tej. But by the definition of the operator T, we already know this is just the number j. And at this point we already see the supremum over j is not finite. Therefore, the operator norm of t can also not be finite. So the first conclusion here is we have an unbounded operator. Therefore, my next question would be, is it at least a closable operator? And in order to answer this question, we will use our sequence property for closable operators from before. And we can combine that with the fact that we have an operator which is not continuous at the origin. So please never forget, for linear maps, boundedness and continuity are connected. Okay, then let's use this fact here for a sequence that converges to 0. So what we can do is to choose a sequence inside the domain of t that converges to the origin. And now we know that we have at least one sequence with the property that the images don't converge to 0. The operator t is not continuous at 0, so this is possible. However, still it could happen that the images here accumulate at 0. But we also know that for infinitely many sequence members that does not happen. So it's possible to choose a safety distant epsilon from 0 and a subsequence x and k such that the images stay away from 0 with distance epsilon. So the absolute value is greater or equal than our epsilon. Therefore, now we can conclude it's allowed to divide by this number. Hence, we can define a new sequence and let's call it zk. So we take x and k and then we divide this by the number tx and k. So this one is definitely a well-defined element in the domain of t. And moreover, if we increase k, we also see that this sequence tends to 0. So in this regard, it works the same as our original sequence xn. However, for the images, something different happens. Namely, we immediately see that we divide 1 by 1, so the outcome is always 1, no matter which k from n we choose. And with that, we now have our counterexample for the characterization for a closable operator with sequences. In fact, we can immediately compare it here. Now we have a sequence in the domain of t, which converges to 0, and the images also converge to a y. In particular, the y in our case is given by 1. And that's already the contradiction, because y has to be equal to 0 if the operator t is closable. And with that, we can make our conclusion, t is not a closable operator. And this also includes that t is not a closed operator as well. Therefore, this is important to remember. In infinite dimensions, we can easily define unbounded operators that are not even closable. But I can already tell you, in this course we will also see a lot of closed operators, so a lot of positive examples. Okay, then I really hope we meet again and have a nice day. Bye bye.